So artificial intelligence is really being scaled rampantly across society, more than even just a year or two ago. It's super prominent now. You take law firms, for example, and artificial intelligence is becoming the core tool that is being used in law firms. A recent study report showed that 79% of legal professionals are using AI. That number bumps up to 89%, depending on which firms you're looking at. Some firms are even AI first, whatever that means. I guess if you come to that firm, they put you through an AI pipeline. It's doing a majority of what can now be automated. People are still involved, but it is an AI first type of thing. What are some other examples? In healthcare, you've got FDA approved AI algorithms. In cardiology alone, you've got 200 FDA approved AI algorithms to help automate and do things autonomously within cardiology. You've got another 1,000 or so within radiology. And just overall, you've got about 2,000, let's say, close to 2,000 FDA-approved AI algorithms in healthcare. Now, again, it's not like fully autonomous. Obviously, doctors, other healthcare professionals still play a role, but that might be more than you realize. And again, these are FDA-approved, so this is absolutely getting pushed through. What other examples do you have? You've got the military, right? The Department of Defense 2026 budget looked for something like $13.8 billion to use autonomous, put research into autonomous weapons, and obviously artificial intelligence would be a big part of that. You've got the Pentagon, which gave $200 million each to companies like OpenAI and xAI and Anthropic and Google and the people who are doing, really frontier model work, because presumably that's going to play a role, and to some extent already is, I guess, in defense. You've got the Ukraine war. And in March, it was like 96% of Russian casualties were from drones, and AI is already starting to play a role in the drone usage. So, what else? I think it was maybe January, early in the year, China gave a demonstration where one individual soldier was able to control like a swarm, essentially, of 200 drones. So it's here, right? It's not just ChatGPTs, it's not just chatbots. I mean, artificial intelligence is absolutely making its way into society. We're scaling it like crazy, and it's scaring a lot of people. Maybe it's scaring you. Why? Well, because it's not just a new technology. It really calls into question, what guardrails are going to be in place, because AI can make mistakes, it can hallucinate, it can do things, and the automation that we're giving it, it's not like some plant factory that's kind of, I don't know, looking at packages or putting nuts and bolts on, and something goes wrong and maybe the plant has some downtime. You're talking about healthcare, you're talking about people's health. If there's a mistake, even if it's only a few, that could be quite catastrophic. And it's like self-driving cars, right? The mistake could be absolutely deadly, it could be fatal to some people. You're talking about military, right? You don't want to have mistakes in these areas. So we're scaling, and this is just this year. So next year is going to be that much more. If I were to go down the same list, that many more FDA approved algorithms, that much more incorporation into military and defense usage, healthcare, whatever, right? So what does that mean? Well, it means that when it comes to the error in artificial intelligence, we obviously have to work super hard at getting the error as small as possible. And again, it's not just like usual technology, like it's always the case. We build technology, we don't want error. If you put a product out into the market, you don't want it to be a piece of crap. You got to get the error down, whatever that means in terms of the infiltration into the market and the usability of the product. If you're doing the assembly line stuff, you don't want error, that's downtime for the company. But again, we're talking about catastrophic, potentially fatal, or society-changing type stuff. So it's really critical if we're going to be deploying AI at the level that we are now currently to get the error down as much as possible. So Brian Keating has a podcast out. He's a professor of California, San Diego, and he does this podcast called Into the Impossible, and he typically interviews notable people, scientists, different engineers, whatever. And he did a interview recently with a man named Roman Yampolsky. And this is kind of like an AI safety guy. You might recognize the name, you might recognize his face. He's been talking about AI safety for a while now, decades, quite frankly. And he's a computer scientist based out of the University of Louisville. And he's written a number of books, but basically this guy has been saying for a while now, and he's really pushing the message now because of all the scalability stuff, like I just mentioned at the beginning. He's saying, it's basically a mathematical impossibility to get the error down completely, or maybe even to a sufficient level, if we go ahead with super intelligence, right? So the idea, it's not that he's against AI. I mean, he does to some extent, I guess, AI, but he can tell and he believes that we're moving towards this notion of super intelligence, right? Like if you look at what AI does, it can read way more scientific papers than humans can. It's already, solving some of those Erdos problems in mathematics. The big names in math, like Terence Tao, is already using tools like ChatGPT. We're using it in healthcare. The Nobel Prize was already, given for the AlphaFold work. We've talked about that previously. It's just doing things at a scale that humans can't do, and in a lot of ways, it seems to be doing it better. We're not there yet, but that's the trajectory. And every year, every month, think about all the new features Claude comes out with every month. I mean, it's just getting better and better every month. So if you look at the trajectory, it seems like we're headed towards super intelligence, right? And you don't even have to, and actually Roman talks about this in the interview. He says, like, I don't even care whether it's conscious or not. I'm not even talking about that. That's a different issue. It doesn't matter whether or not it's conscious. I mean, it might matter for other reasons. But for the sake of what we call super intelligent, it's producing outputs the way people produce outputs. So that's super intelligence, right? If it's going to do it at a level much better than humans, and it looks like that's the trajectory that we're on. So he's saying, okay, interesting. But he's saying he basically wants to put a moratorium, kind of a halt, or at least a really big slowdown on this trajectory towards super intelligence, because he's saying, look, you can show essentially mathematically, you can prove that there's just no way to get the error down in super intelligent. You might reduce it somewhat, but you'll never get rid of it. And remember what I said, when you look at the errors that occur in super scalable AI, that would be super, even just right now, like in self-driving cars, it's absolutely catastrophic. If you're going to do it in healthcare, an error is going to be really, really bad. If you're going to do it in the military, right, these error, it almost doesn't matter how small you make it, any error at all, some people might say is just completely unacceptable, right? It's just so catastrophic. Regardless of what you, and even if you think, well, no, I mean, I don't really agree with that, because if you take self-driving cars, for example, and you say, well, if it's 10 times better than what humans are doing, yes, there's still going to be error there, but it's 10 times better. So statistically, it's still a better thing. But and that's true, but keep in mind that we're scaling this bigger and bigger. It's more embedded in society. This is just 2026. Imagine 2030, imagine 2040. It's just going to be everything and everywhere in some sense, arguably. So even if there is this boundary, if there is this cap, and who's to say where it is, where you can't squish the error down small enough, and there's always going to be that level of error, what does that mean? And I guess Roman's point, the Yampolsky, is that we're going to never really be able to control this thing that is much smarter than us. And that's a problem, right? Like, you would think that the most intelligent entity on Earth would have control of the other things. Like, I guess that's what people are, right? Human beings have control of the other animals. You essentially have control of your children, right? Now we're bringing something that is on a trajectory for super intelligence. It's going to be that much smarter than we are, but we don't have the control it does. Or there's just no way to step outside the system and look from the outside in and say, okay, if this goes wrong, we can do this. If this goes wrong, we can do this. He's basically saying that's impossible. So we need to kind of put a moratorium on this, slow it down, step back, or just not do it at all. And he actually makes this statement, and he has a statement right out of the University of Louisville where he published, and basically is saying that if we cannot, if somebody, scientist, engineer, computer scientist, whatever, if they can't come forward and prove that we can, basically safely govern, or more to the point, prove that we can get the error down enough or completely on super intelligence, then we shouldn't be doing it. Because once you accept that there's always going to be that level of error, and it's a mathematical guarantee, then this is a real big problem. It's almost like it guarantees our own demise, so to speak, regardless of what that means, whether that's like a Terminator 2 scenario and the AI decides it doesn't need humans anymore, or it just causes, with whatever guaranteed level of error it has, it just causes these types of catastrophes. And because of the scale that we have AI at, this is just super, super problematic. And Yampolsky, Roman Yampolsky, is basically, where does he get this? Like, why would you say it's like mathematically impossible to get that error away from AI? It's just always going to be there, and we're scaling the systems. Like, what math? What are you talking about? Like, you're just making that up? Well, that's coming from basically these kind of undecidability problems from computer science. It really goes all the way back, you could say, to Kurt Gödel and his incompleteness theorems. And the incompleteness theorems, you can kind of summarize it as any sufficiently powerful formal, any sufficiently powerful, consistent formal system has true statements in it that cannot be proven to be true within that system. That's one way to put it, okay? And I'll explain that a little bit more in a second. And then you have kind of Alan Turing, which is kind of basically just extending what Kurt Gödel did. He's extending it in a computational setting. And again, just kind of the colloquial definition to put around that, it's basically saying there is no algorithm that can decide for every possible program whether or not the program halts. So it's kind of like, you'd think you'd be able to know for a program, if you had an ultimate computable substrate, it would be, if it was the most powerful thing in computing you had, it would be able to know for any other program whether that was going to just kind of keep going in a loop or whether it was going to stop or some other issue related to what it would be able to decide. It's got a limit on it. And and I'm not going to, break apart all of the Turing stuff and all of the Kurt Gödel stuff. I've talked about this in other episodes, right? But it's just a little bit more to push on that. It's this kind of contradictory scenario that pops up via recursion. Okay, so it's in the Gödel setting, Kurt Gödel, he basically makes a mathematical version of, this statement cannot be proven true or something like that, right? And it's like, well, if it's true, then it's wrong, but then if it's wrong, it's true. And you get into this kind of contradiction. And Turing is basically the computational version of that, and I'll put some links in the description. You can go look more. You can go look it up yourself. You can go ask ChatGPT. You can get into conversations about it. The take-home message here is the limitations in mathematics and in really any axiomatic type formal system, including computation, they occur because there's this recursion. There's this ability to step outside the system at a meta level and create something that system itself cannot compute, cannot answer. So in math, it's kind of like, no matter how sophisticated and advanced we get in mathematics, you can kind of just casually say there's always going to be things that math can't do. Just like a real casual way to say it. In the case of the Turing, the computability stuff, there's always going to be stuff that a computer is basically just not going to be able to calculate or not going to be able to predict. It's never going to be fully able to predict or compute its own behavior, or us using the computers are never going to be able to do so. So at the end of the day, whether or not any of that made sense, you have fundamental, mathematically proven results in mathematics and computing that say these formal systems, whether it's math or computing, they can only go so far, right? They can't calculate everything. There's no way you're going to be able to exactly predict the outcome. There's always this kind of black area, this gap that you're not going to get past. And so Roman Yampolsky is basically using those types of undecidability and impossibility and kind of verification type results from computing and mathematics to say, look, this is what we know about computation, right? And we use computation to do artificial intelligence. So you draw the arrow from computation to intelligence, artificial intelligence, and then you say, well, if the impossibility is in computing, then I guess that impossibility is in AI as well. And so if you go to scale it, no matter what you do, no matter how much we try to control it, we're never going to be able to really control superintelligence. And that's a problem for all the reasons I mentioned already. Okay, so that's Roman Yampolsky, and that you go check out that interview. I'll put the link in the description with Brian Keating on Into the Impossibility podcast. And so this is, kind of like not great, right? Like this sounds bad because we always hear the usual kind of, well, AI is not, it can make mistakes and it can hallucinate. And what about this? And you can kind of push back and say, yeah, but it's getting better every day. And then you can say, yeah, push back the other way, but it's getting scaled. And, and it's kind of just, well, I don't know, I guess maybe we'll squash those errors eventually, or we'll get them down to an acceptable level. That's just progress. That's just technology. Is that really ever different than that? But now you've got this computer scientist coming out, this well-established guy, and he's like, no, it's like a mathematical certainty, basically, right from the core of pure mathematics and computation where we can show that you're just never going to really be able to control this. You're not going to be able to predict the outcome. It's just not doable. Again, like what the level is, is there a level of acceptance there, or is it just completely unacceptable? Roman almost seems to lean on the side of it's just basically completely unacceptable, but I think at the very least he's saying, out of humility, he's probably like, well, I don't really know for sure. We see this mathematical impossibility result. All he's saying is, let's not build this stuff unless, and then he sets up this condition that we'll see is essentially impossible, unless someone comes forward and proves that you can actually control these things. But he knows, I know, I'm telling you, if you don't know, that isn't going to ever come forward, right? Because we have these proven mathematical results already. So the condition he's setting up that would allow us to go to superintelligence is not going to be a realizable thing anyway. So, take-home message there is Roman Yampolsky is basically saying, do not build superintelligence. You can use AI, we can use maybe like chatbots, we can still use it for drug discovery. I think he's all for that. Let's not continue this trajectory towards superintelligence and embedding it in all parts of society, because the error is not going to go away. Okay. So now I'm going to push against this. I'm going to de-hype this a bit. And actually, I think Roman Yampolsky is making a fundamental error here, a mistake in the type of error he's talking about. The type of error he's talking about is true. It absolutely exists in computation. The problem is you can't take the error that's in Turing machine computation and then just implant that into AI and say, yeah, that's the same thing. Like there's just this direct connection between what goes on in computation and what goes on in AI. Even though that sounds like, what am I talking? Of course it is, right? Like we do artificial intelligence on digital computers. If digital computers have these limitations, then so does AI, right? Wrong. And I'm going to tell you why that is. That connection is actually much more of a disconnect, fundamentally disconnected. And I think Roman, I'm going to argue, is making that mistake. Okay, so first of all, let's go ahead and define error in artificial intelligence. Because I'm saying that word. And now I'm kind of pulling away from the error that Roman was talking about. Okay, let's just put that aside for a second. We'll come back to Roman's approach in a bit. Let's just talk about artificial intelligence proper. Okay, so what is error? Well, it's basically the difference between whatever the model is predicting and what the truth is in the real world, right? Like if you're talking to ChatGPT and it outputs something, and is it telling you the truth? Well, there's some distance there. Always, right? Hopefully it's small, but there's a distance between what it's telling you and what the absolute truth is, right? It's no different with humans, quite frankly. But in AI, this is a statistical thing, okay? And more to the point, when you calculate the error in artificial intelligence, this is not something that you can kind of point at and say, well, there's where the error comes from. This is a distributed population level multi-instance thing. You are taking large sets of data and you are calculating that distance between the model output and whatever reality is. Reality would be encoded in the data as well, typically as labels. It doesn't matter, right? It's in the data as well. So you can calculate the distance, but that distance is not between like two individual things, right? It's between millions and millions of population level statistics. And so, and it's between millions of things and millions of things. It's between millions of things that the model is predicting and millions, if not billions of things that serve as the ground truth, and there's a distance between them. Okay, so why am I saying that? Why is it important to understand AI error in that sense? Well, that error is not like a localized thing, like I said. The only way to truly understand error in artificial intelligence is at the population level. So the population would be like, whether it's people or the population of all the data. It's a statistical thing. It's a system level thing. It's a multi-billion parameter configuration level thing. It doesn't exist as an individual thing. It's not something you can point at. Okay. Now, who cares? Why am I talking about that? Well, what I want to now impress upon you is that when we talk about scaling AI, like it's this brand new technology, right? It's automating the white collar stuff. It's not just the blue collar. It's completely different. It's going to change this, change that. There's a lot of truth to that. But in many ways, when it comes to error, this is not new. This is something that society has already been doing for hundreds of years, actually. What am I talking about? Well, if you take a look at companies, for example, right? Corporations in society are the same type of distributed error, nobody specific is responsible type system. That's what a company is, right? When we give our money to a company and we do whatever in society and they're giving us a product and there's this transaction, let's use an exact example. Let's say a company dumps a bunch of poisonous garbage into the river. You can say, okay, who's at fault? Well, who is it? Is it the CEO? Is it like stakeholders? Did somebody make a specific decision? Even if you point to the person who pulled the lever and said, okay, go ahead and dump, is that the person who's at fault? It's not so simple, is it? Because while they were having conversations with other people and maybe somebody was above them and maybe they kind of said and they kind of said, it's distributed. The idea that you can exactly demarcate where decisions came from in a company is actually not true. In fact, that's the entire point of a company, right? Limited liability, the whole point is to detach error from the individual. It's the literal point of a corporation. It's the point of a company, is to detach error from any one individual. So you can't point So this notion that we're putting something into society where the error is kind of distributed, and you can't say who. It sounds like this dangerous thing, and it sounds like it's unique to AI, but it's not. We've been doing this for hundreds of years with corporations. We've been doing this with government. The government is the same thing. You can blame the prime minister, you can blame the president, you can blame an MP, you can blame whoever you want, right? It's not how it works, right? Those are just levels of representation that are sitting a bunch of millions and millions of votes, and on and on. You can't point at any one vote. You can't point at any one thing. Countless interactions. The causal web is absolutely distributed. And we do this and we trust the government. Now, again, I'm not saying corporations are perfect. I'm not saying governments are perfect. They're absolutely not. But the point is, we've been doing this for hundreds of years. We do this in society. It is not particularly unique to AI. Okay, you can do this with scientific communities, right? Scientific communities, right? The errors occur in science all the time, and sometimes those errors can propagate, for many, many years, maybe even decades, and then finally something gets realized that this was wrong and this is not good. Why did that happen, right? There was like a genetics example where people were misplacing something on the Excel spreadsheet, and it went years, and all of a sudden, wait a second, these results are wrong, right? There was that microplastic example where it turned out to be the nitrile gloves. And why do these errors go so long? It's like you can't really point at any one person. It's the ecosystem of science. It's the different incentive structures. It's not necessarily, sometimes, but usually not anyone trying to do anything nefarious. It just emerges, right? It's an emergent population level, just like the spread out statistics of error. That error is something that is spread out. You can't pinpoint it. Okay, so corporations, governments, scientific communities, the market itself, right? Same thing, right? If you get a bubble, it's not like the bubble occurred because of that person, or the crash happened because that one investor. It's just not how it works. You might get stories like that, but those are fairy tales. That's not how it works, right? There's just a near infinite web of causality that you can't disentangle. You can't pick apart. It's distributed. And David Runciman, actually, in his book, The Handover, makes this point, and he does a really good job of saying, if you take a look at the state, right? Like if you take a look at governments, if you take a look at companies, right, we all talk about AI as though it's this brand new thing, and like now we're handing over control to this machine, and it's smarter than us. Yeah, so is a company. A company is smarter than any one person, right? So is scientific community. So there's no one person that's even remotely close to the level of intelligence of these collective phenomena, which is of course true, and it is intelligence because they do make decisions. It's not people. A company isn't people making decisions, right? Like people do make decisions, but that's not the output. The output of a company is not individuals making decisions. It's the company making decisions. It's its own entity. It exists at the system level. Okay, this is factual, right? This is true, right? And again, that's why the company was started. There's advantages and probably some disadvantages to doing that, but that's what it is. That's why we form a government, right? That's why we have scientific community. That's why we have the free market, right? The market makes decisions. It doesn't mean there's no, and we'll get into the levers that do get pulled, right? Where they want to talk about interest rates and things like that. But it's the market ultimately that makes the decisions. It produces the outputs. You can't trace it back. So this is not new. This notion that artificial intelligence, Roman comes up and he complains about it. It's like, wait a second, right? Artificial intelligence, this is going to be a superintelligence. And it's going to be smarter than any person alive. And we're not going to really have control over it. Yeah, that's not new. Nothing about that is new. That's exactly what we've been doing with companies, with governments, scientific communities, with markets, and all the examples I get on any collective phenomenon is exactly that. There's a level of uncontrollability. You can't predict what the market's going to do, right? Otherwise you'd be making billions of dollars and getting all the stock choices correct, right? You can't predict exactly what the market's going to do. You can't predict exactly what the government, you get all the examples, right? Companies, we just don't know. It's the same thing. It is the same thing because it is a collective phenomenon. The error is distributed. Okay? Again, go check out David Runciman's book as kind of a good talk on how there's no difference really between the AI and those examples. Okay, so we kind of come to this realization that when we look at error, and I'll get into, remember I said at the beginning, like Roman Yampolsky's version of error is not even the right error. Just hold on to that for a second. But even just error itself, it's not a bug, it's a feature, right? Like, in other words, for any true superintelligence to exist, or any type of intelligence, what we would consider intelligence, error is absolutely a necessary ingredient to it. It's a hallmark that it actually exists, and it actually is a participatory ingredient in making it possible. Just think about yourself. You're an intelligent human being. Well, why are you intelligent? What is it that you do that's intelligent? You get good at something, you develop skills, you speak really well. Well, there's no way that would have happened without a great deal of error. That's part of the trial and error, which is absolutely core to the way complexity produces intelligent outputs, right? Error is absolutely part and parcel of intelligent systems. So right off the bat, it doesn't make sense to kind of step back and be like, well, these AI systems are going to have error, and what are we going to do about it, right? That this is a problem because we're getting, no, I mean, not to say that they can't cause problems, but this is nothing new. And this is further to the point. If you were to actually squash the error down and make the system completely predictable, you would no longer have, by definition, artificial intelligence. Because by definition, intelligent systems have error as a critical ingredient to them. It's part of the trial and error they use. Deep learning uses trial and error when it does millions of iterations and uses backpropagation to constantly adjust its parameter values to produce the output that's needed. Okay? Markets feedback on themselves, and we'll get into this recursion stuff later. This trial and error is right in the name, right? Like, it is part of what intelligence is. So it's kind of like saying companies make mistakes all the time. This is unacceptable. So until someone comes and proves that a company can't make a mistake, we got to get rid of companies. No, that's stupid, right? Like, that's just dumb. It doesn't make any sense. Until we can prove that the market can't form a bubble, and we can, mathematically prove that there's no way for the market to crash or whatever it is, then we shouldn't be doing, I don't know, we shouldn't have an economy, we shouldn't have a free market, let's go back, let's go top-down control. No, right? It is the same thing, right? Now, so this brings us kind of to the core problem here. And again, I want to say the outputs that the market produces are emergent outputs. The individuals of the market don't produce the outputs. No individual sets the price. Nobody sets the price in the market. Okay, this is going to be relevant to the problem with saying, since Turing machines apply to computation, therefore Turing machines apply to AI outputs. No, they don't. Not at all. It's completely disconnected. It's not even it's a complete category error. Individuals in the market do not set prices, right? Individual decision makers in the government, even though some, depending on how corrupted and all that, in a well-running government, in a well-running collective system, are not really making decisions. It's a collective thing. They make decisions all the time, but at the output level, that's not the decision that gets produced. Okay? Scientific communities, all the other examples. The emergent level is fun, just like the error. The emergent level is there's causal closure between the emergent level and the underlying substrate that it runs off of. Right? Ant colonies, right? Use this example a lot for complexity. They find out these amazing pathways between A and B. Okay, and you can say, well, how do they do that? Is it because of the ants? No. What do you mean? No, of course it is. They're ants, right? Well, it's not because of the individual ants. The individual ants are just doing dumb little local rules. They detect pheromones, they kind of dodge each other, whatever they're doing. Out of that emerges the decision-making process to find and solve categorically hard problems like the shortest route between paths. Termites do these amazing kind of engineering feats, what we would consider engineering feats with thermal regulation within their mounds and all this stuff. No termite understands or knows what the heck thermal regulation is, and yet they achieve these. It's a distinct phenomenon. It's distinct levels of the phenomenon. Okay? So I have two objections to Roman Yampolsky's take. I mean, the first one is he has the wrong standard. He's asking for basically proof that the error has been eliminated in systems where that just simply doesn't apply. It doesn't make any sense. Like I said, you're not going to eliminate the error in a company. You're not going to eliminate the error in a government. You're not going to eliminate the, right, whatever, the free market. It just doesn't apply. It doesn't make sense. There's no such thing as a proof in that space, right? It's just these examples where people get super reductionist. You kind of myopically do what you do in computation, and you notice some pattern, and then you implant it into the real world, and then you think it still applies, and it's just not true. It's goofy, actually, right? Turing machine is a very specific thing. It doesn't apply to this real world situation. It applies to, and the reason why you might make this mistake is because information age has been based primarily on digital rules-based computing, right? So it was modeled very well after a Turing machine, but the outputs that AI produces, that's just not true. I'll get more into that in a second, okay? The outputs are emergent. The emergent level outputs that AI produces is not modeled as a Turing machine. That doesn't make any sense. Okay. The substrate that it runs off of is a Turing machine, but the outputs that it produces are not. Remember the difference between the ants and what the ants produce, the difference between the voters and what democracy produces, the difference between, right, people making stock bets, whatever, and what the market actually does, right? Two causally closed different levels. Okay, so the standard doesn't make sense. You need to prove that's not how error works in these systems, right? It doesn't make sense to say you need until somebody comes and proves this thing that absolutely doesn't apply to the system, only then should we build the system. What? Doesn't make any sense. Two, so I've got the first objection is the standard doesn't make sense. Two, it's the wrong ontology. Okay, because again, what I've been saying, he takes computation and then draws an error to artificial intelligence. And so whatever you find provably in computation must apply to artificial intelligence. No, that's not correct, right? The Turing machine computation that we use, so do we do that to build AI? Yes. Okay, so can't you draw the arrow? No. Same thing with the ants and the termites and the markets and everything else. That is the substrate. That is the scaffold that we put in place to make artificial intelligence happen. Right, so let's just say like matrix multiplication. That comes from linear algebra. It's a major part of the mathematics that gets used to basically mush the data together, to mix it and match it so that we can eventually create these outputs at the emergent level. The matrix multiplication, though, is not producing the outputs. That's just getting all the ants together, right? That's just, I'm going to mix and match all these ants together. I'm going to mix them a certain way. That is not the output. So matrix multiplication would be happening at a substrate level of computation as a scaffold to AI in order to get the data to mix and match the way we need it to mix and match, right? But that is not the same as the emergent level outputs that deep learning produces in AI. In fact, they have pretty much nothing in common at all. I can give you, you can mix all the ingredients of a cake deterministically, but that has nothing to do with the way the cake's going to taste. I mean, the ingredients affect the way it tastes, but the actual experience of tasting it has nothing to do with you mixing the ingredients. You understand what I'm saying? It's a completely different output. It's a completely different phenomena of what's occurring. You can't trace it back. You can't trace the taste of a cake back to some specific exact ingredient. You can't, right? Well, it tastes a little bit like cinnamon. Yeah, but it's not just cinnamon. Well, it's sweet and it's cinnamon. Well, sweet and cinnamon is kind of vanilla. Well, it's kind of that blend, that synthesis is its own thing. It's not more, it's different. That's the point of complexity. So we've got his standard, which doesn't make any sense, and then we've got this ontology that's just wrong. It's not computation pointing to artificial intelligence, it's computation pointing to emergence, at which point Turing machine is now gone, and that produces the artificial intelligence. Okay, now here's the other thing, and I think this is really interesting. When Roman is talking about the this kind of undecidability, this ultimate limit that we get from Kurt Gödel and Alan Turing, right? These computational results. Well, here's the other thing. Not only is that like the wrong error to be talking about, actually that's not even a limit. That is what gives rise to the very complexity that we need to allow intelligence to happen in the first place. In other words, the thing that Roman is pointing at and saying, this is a problem for AI, that's not a problem for AI, it's what makes AI possible. Now, that might sound a bit confusing to what I just said before, because I said computation doesn't point to AI. Here's the thing. Computation points to emergence. The limitations in the computation are what allow the emergence to happen in the first place, which then produces the output. So let me give you some example. This has to do with the recursion. Right? People in computer science that are just looking at kind of Turing machines and these undecidability problems, they're noticing that this self-reference is causing the problems, right? The self-reference means you can't prove everything in math. The self-reference means you're not going to be able to compute all behaviors, whatever it is. But that self-reference is what allows systems to fold in on themselves and to tangle into such an extent that you produce genuine complexity and produce emergence. And notable people understand this and have written about things like this. Gregory Chaitin understands this, right? Douglas Hofstadter, right? You know, he calls it the strange loop. You can go look at the television show Westworld. They've got the scene where the guy's tracing out, it looks like a maze. I think it's inside the head of one of the androids or whatever they're calling them. And he realizes it has to do with keep circling back, you know, itself, something to do with self-reference. Self-reference is the absolute critical ingredient to intelligence. Critical ingredients, because you need complexity to get intelligence. You get complexity from self-reference. Okay, so why does that happen? Well, think about a Lego brick. You can essentially create an infinite number of different things with Legos. Why? Well, because the Lego brick itself is limited. There's only, so many studs and so many whatever you call them, and you can only put them together in so many ways. That limitation is what allows for the immense level of creativity. It's the constraint that allows things to keep folding back in on themselves. Think about language. Language has constant self-referencing, and it kind of eats itself and eats itself and eats itself, because there's only so many, let's say, words, and words can only do so much. They can only hold so much meaning. But because of that limitation, you're able to actually fold back in on yourself and keep referencing yourself. If individual words had infinite meaning, you couldn't create anything with it, right? There'd be no limitation to the words, and so you can't reference a thing because the thing doesn't exist. It's already infinite, right? It's like the Lego brick. If one piece of Lego was infinitely, you could articulate it in all these kinds of different ways, it would be much harder to actually get creative with Lego itself. You need the constraint so that there is a system in place in which many things can come together to create a massive entanglement of genuine creativity. If individual words in a language had infinite meaning, you couldn't reference it because there is no it to reference anymore. Okay, it's the same thing. Markets are self-referencing. You can show that, right? Again, governments, all these complex systems. It's the limitation imposed by the undecidability that allows self-referencing to happen. And it's that self-referencing that leads to massive expressibility and creativity in complex systems, which is absolutely the first critical ingredient to achieving genuine intelligence. Okay? So Roman Yampolsky is pointing at something as though it's the problem. We have this mathematical proof that we're never going to be able to, control AI. Again, one, the error isn't even the same error that we have in AI, so it's not even really related. And two, the thing you're pointing at is actually what allows the substrate of computation to produce genuine complexity, to allow us to have AI in the first place. If you took that away, like you're suggesting we should, you wouldn't have intelligence. You have to have the error. You have to have the limitation. The limitation leads to recursion. That's what intelligence gets us. That's what gets us intelligence. Okay, so again, he's going from computational substrate. Yes, we start with that in AI. And then he connects it right to AI and say, whatever limitations exist here exist in AI. No. We have computational substrate. Yes, we scaffold AI. We set it up so it can do millions of iterations. That's all standard rules-based programming. But then we let it go. And then it does recursion, millions, if not billions and billions and billions of times. That leads to emergence. That produces a different level of output. The output is not produced by the Turing substrate. The Turing substrate and its limitations allows complexity to exist, and that's what produces the output. Okay? So, with all that said, what does that mean? Going back to the beginning, I talked about scaling AI, and there's this error. So again, the fact that we're doing this already in society with companies and markets and all that, the question is, so what do we do for control? Well, what do we do for control in companies, right? They're not perfect. But we found a way to essentially manage them in society successfully for a very long time. Here's the key point. It's actually easier to predict emergent outputs than it is the underlying substrate from which it arises. Okay, think about this. It's easier to predict temperature, pressure, and volume than it is to predict the individual molecule trajectories that give rise to pressure, temperature, and volume. There's actually fewer levers to maneuver in a complex system, right? And it's actually easier to predict what's going to happen than it is to try to go into the specific details and know exactly what's going to happen. So if you think intelligence is coming from the underlying Turing substrate, the Turing substrate is the super detailed, this and that, and we can't predict it. No, I know you can't predict it. You don't need to predict it. That's not what emergent output is. That's not what AI is. That's the setup for AI. That's not the outputs of AI. The outputs of AI come from complexity, and there are levers to do that. And we see that with markets. There are levers, interest rates, whatever it is, the Fed can kind of put in place. It's not perfect, but there is some level of control. There are levers for scientific communities. There are levers for companies, obviously, right? There are things that can be done at a higher level, typically a meta level. Again, think about the volume, pressure, temperature example. Those do become, from statistical mechanics, those do become much more predictable than the underlying details. So when Roman Yampolsky tries to make that connection between the Turing machine and the emergent and AI, if you look at it like that, you're right, it is unpredictable. Because the Turing machine is unpredictable. The model that you're using, the type of error that you're dealing with does have that. But that's not what AI is. Okay? It's not Turing substrate, again, right, to AI. It's the Turing substrate to emergence to AI. The error is distributed. It's a different type of error altogether. We already do this in society. And you want the self-referencing recursion that you are calling a problem, because that's the only way you're going to get the intelligent outputs to begin with. Okay? So that's it for this episode. I hope that made sense. Go ahead and ask questions on social media, or go ahead and check out Dekion.io to get more into these types of concepts, to ask questions on the community forum. You can ask AI. There's 2 different AI features now on the Dekion platform. One is you can ask the episode itself and ask questions. Tell me more about this Turing, or what did Sean mean when he said this? You can keep digging it, spend time with it. You can do cross-episode connections, and there's all kinds of data visualizations. And then the other AI feature that I just added is you can actually, if you're trying to achieve a certain goal, like a certain learning outcome, let's say, in a particular area of science, or you just want to know something better, it'll bring back techniques to help you achieve that, and it will reference the episodes that those techniques kind of draw on to help you achieve that goal. Anyways, go ahead and check out Dekion.io and open the Science in Perspective app store. Okay, thanks everyone for listening, and for those of you who are watching, until next time, take care.